We need to start talking about another type of differentiation, which is called implicit differentiation. We use it when we have an equation in an implicit form, which means our dependent variable isn't explicitly written by itself, like in this explicit form. So here would be an example of an equation in explicit form. Here would be an equation of an example of an equation in implicit form. So remember, before we've talked about all the different ways of saying differentiate or derivative. dy dx specifically means the derivative of some function y with respect to x, which means as x changes, x then causes y to change. So what's my independent variable, what's my dependent variable is basically what it comes down to. So if I wanted to, if I differentiated this first example, I could say y prime, but I could also say dy dx equals 9x squared minus 8x. Saying dy dx is the same thing as saying y prime. We are going to do a little bit of a switch where we're going to start using dy dx. And basically it just tells the reader that I'm differentiating with respect to x. X is what's causing y to change. When we do implicit differentiation, we are going to differentiate both sides with respect to x. So if a term has a dependent variable, we have to be assured to attach a dy dx, which again tells the reader what we're differentiating with respect to. This will make more sense when we start doing some related rates problems where we talk about, for example, the radius changes as time goes on, or the volume changes as time goes on. So it'll have a little bit more concrete meaning once we get to some more applied problems. From there, we're going to collect all the terms with dy dx on one side and solve for dy dx. So I have three examples, one that uses implicit differentiation only, one that combines implicit differentiation with the product rule, and one that combines it with the chain rule. So looking at example 1. So I'm going to go ahead and differentiate both sides with respect to x. Well, I know the derivative of 7x is just 7. 4y squared. So if I differentiate it in the same way I would differentiate an x, I would get 8y. But because that is my dependent variable, I have to tack on dy dx to show again that y is changing as x changes. Plus, doing the same thing with 3y cubed, I get 9y squared, again tacking on that dy dx, since that is, again, my dependent variable. From here, that's step 1. From here, I'm going to do step 2, which is to collect all terms with a dy dx on one side. Well, that's already done. And then I have to solve for dy dx. Well, if I wanted to solve and get these dy dx by itself, the first thing I notice is, well, these two terms both have a dy dx, so let's factor it out. And once I factor it out, I can then divide both sides by the 8y plus 9y squared, giving me 7 over 8y plus 9y squared equals dy dx, which again is the same thing as y prime, and that will be my final answer. So the big thing is tacking on that dy dx to all your dependent variables. Let's look at another example. So first thing I want to do in example 2 is differentiate both sides with respect to x. Well, the very first thing I notice when I go to differentiate this is that I have a product right here. So I'm going to have to use the product rule. Well, then I'm going to let my first function be x squared, and the derivative of my first function be 2x. My second function is then y, and the derivative of my second function is 1 times dy dx. Again, I have to tack the dy dx on. So now that I've established that, I have that little setup, I'm going to go ahead and actually differentiate this example 2. So using my product rule on that first piece, I get the derivative of the first times the second. So I get 2xy plus the derivative of the second times the first. So x squared dy dx, since it doesn't matter what order I multiply, and I'd rather have the dy dx in back. Differentiating my next term, I get plus 3y squared dy dx equals 0. Do not forget to differentiate the right side of your equation. I would run into that issue. I've run into that issue for students in the past. Now from here, I want to get dy dx's all on the same side. Well, they're already on the same side, but I want to get rid of that 2xy, so I'm going to have x squared dy dx plus 3y squared dy dx equals a negative 2xy. Again, like the last one, I can factor dy dx out. Oops, and then I didn't, let me fix that. Oh, I can't erase, so I'm going to scribble it out. I'm getting ahead of myself to write out all my steps. Now that I have dy dx factored out, I can go ahead and divide by the x squared plus 3y, giving me dy dx equals a negative 2xy all over x squared plus 3y squared. And there isn't anything I can reduce, and I've now successfully used implicit differentiation while also using the chain rule. So notice those implicit differentiation rules apply during that as well. Looking at one more example where we have the chain rule involved. And if you want to try one on your own, this would be a good one to try. First thing I'm going to notice is that I can easily differentiate cosine of x. It's just negative sine of x. However, when I go to differentiate this piece, I see I have an outside function, 3 times sine, and an inside function of 2y. So I'm going to go ahead and say my inside function is 2y. My outside function is 3 sine of u. My u prime then is 2 dy dx because of the y. My v prime is going to be 3 cosine of u. So I differentiate my cosine first, and I get negative sine x. After applying my product, or excuse me, my chain rule, I'm going to distribute the minus sign after if necessary. I'm going to have y prime times v prime, so 2 dy dx times 3 cosine of, and I have to plug u back in, so I'm going to say cosine of 2y, equals, differentiating the right side, 2x. Cleaning this up a little bit, I get negative sine of x minus 6, multiplying my 2 and my 3, cosine 2y, I'm going to put parentheses around that to show I'm taking the cosine of the 2 and the y, dy dx equals 2x. From here I can use some basic algebra to get dy dx by itself. So I'm going to go ahead and add sine x, and I'll be left with negative 6 cosine of 2y dy dx equals 2x plus sine x. And I will divide by negative 6 cosine 2y, giving me dy dx equals 2x plus sine of x all over negative 6 cosine of 2y. And again, that would be how I would use my chain rule along with implicit differentiation. Again, noticing just like with the product rule, I did have to still use within kind of my inside work, I still had to keep track of that dy dx with any of the dependent variables.